In this episode, we're having a conversation with Professor N. Swaminathan, who is a world-famous scientist. He's a professor of mechanical engineering here at Cambridge. His work focuses on green and silent combustion and really addresses one of engineering's biggest challenges. Beyond the lab, he's also a fellow at the Royal Academy of Engineering, educating and helping inspire the next generation of engineers. Hello and welcome to the EduCon Podcast, where we speak to higher education institutions who are actively working and changing the global education landscape. Today we find ourselves at Cambridge. My name is Janhavi and this conversation was brought to you by Skoda and Java. Professor Swaminathan, welcome to our set. Thank you so much for your time today. Really looking forward to the kind of conversations we're going to have during this particular conversation episode.
Thank you very much for having me here. Look forward to our discussion.
Of course.
And I will see how we can help other people to understand what I'm trying to do.
Absolutely. First of all, congratulations. You've just been elected fellow at the Royal Academy of Engineering. How does that feel?
It's great. It's great. It's the highest honor in this country. The fellowship election is very 1 year long process. It's involved. So some of the ex-fellows or the current fellows have to nominate you, and that nomination has to be supported by world experts across the globe to say, what he has done makes an impact. Mm-hmm. It's not just the publication, it's the impact, the engineering impact it creates in the industry is what earns the fellowship. I feel very happy about it, and I'm quite honored to be in that position, in that place. And I thank the Academy for electing me to be the fellow.
Fantastic. You've worked quite a bit, and your research has centered a lot around low emission and silent combustion. Yeah. Can you talk to me a little bit more about that? What do these words mean?
For example, basically what we do in the car, we burn petrol, right? Mm-hmm. So any petrol is hydrocarbon. Hydrocarbon means it has got carbon, hydrogen in them. So when you burn carbon, it produces carbon dioxide, which is a global warming gas, which we all hear about through various medias because of the climate change and whatnot. And then hydrogen, when you burn hydrogen, it produces water. Yeah? The water is also a greenhouse gas, but it condenses out, so it becomes a liquid. So it's not as critical as CO2. That's why we don't want to burn hydrocarbons, and we want to move away from zero carbon fuel, having only hydrogen, for example, or ammonia. So we can completely get rid of the problems of CO2 if we can, but practical applications, doesn't allow it. So the power density means the amount of power you produce per kg, per unit mass of the fuel has to be large. That means you can carry a smaller amount of fuel for a longer distance. This is very critical for airplanes, because heavier fuels means heavier airplanes. Airplane industries, they want to put more number of people, make everything light, so they can make more money.
Yeah.
So to address all of these bigger problems, we need to come up with a science which can help us to burn hydrogen, remove carbon dioxide in the safest possible way, in the most efficient way. And that's what my research is focused on. And also I closely work with companies like engine manufacturers across the globe. Many companies from America to Japan, including UK, there are many engine manufacturing companies. I work with them. And also you also brought up another term, which is the silent combustor. So what does that mean? Do you cook at home?
Yes, I do, in fact.
So when you turn on the gas off, what do you hear?
A little bit of a sound, isn't it?
Yeah. So what is that's a spark.
Yeah. Okay.
After the flame is lit, you will hear a buzz. A big buzz will be coming out. Low frequency noise will come out. Why is that coming out? Because the gases are expanding and shrinking in a very fast-paced manner. And that expansion and shrinking creates a sound wave. And that's what we hear. And that's known as combustion noise. Okay? So if you take that flame and put it in a tube, then it can sing as well.
Oh, wow.
Because it depends on the frequency of the noise, whether the frequency matches with the natural frequency of the sound tube, or the tube which is enclosing the combustor, then it can amplify the sound. And that can become a very major problem for airline industries and aircraft engines. Sometimes it can break the engine completely. Mechanical failure can happen, and then the people don't want to have that. So what these engine manufacturers will do is they will try to control them. If they see that's going to come up, they will turn on some controllers, electronic controllers. They will change the fuel flow rate or airflow rate, or do some simple measure to control or to suppress the pressure oscillation. And that IP, or the intellectual property, or the idea behind how they control these pressure oscillations, is a billion-dollar industry across the globe. Nobody wants to share that with anyone else because it's protected knowledge. But what we do in our lab, including my colleagues and many colleagues in my university, we try to understand this problem from the fundamental perspective and then look for ways how we can eliminate it by design. Yeah? Rather than having controllers, if we can eliminate it by correct design of the machine, then we save quite a lot. Yeah? One. And why are we interested in? Because in the future, specifically in the UK, many of the airports are thinking of charging airlines based on the noise that the aeroplane is going to make when they are taking off. So if the aeroplane is going to make a bigger noise, they have to pay a higher penalty, higher levy to the airport. So that means they will lose out their margin. The airline will lose out the profit. So by making the engine silent, then it helps the engine manufacturers to sell more of their engines. The airline will be very attractive to those silent engines. So it's all embedded in how much money, where, and how it flows, who makes the money, all the things. But fundamentally, it is related to the sound, how the sound is produced by the flame or by the combustion process, and how that sound interacts with the geometry of the combustor, where you are enclosing the flame. So that's why this problem is very interesting from a fundamental perspective and very close to the practical applications for various fields, as I said, yeah. So that what challenges us to explore this.
Fascinating.
And then you can see I'm smiling when I talk about it. It's a very, very interesting field.
Yeah, I'm sure. So then through your research, have you come across any findings that really perhaps stunned you or maybe made you think, oh, I didn't think that it would go that way, in fact?
That's an excellent question. I think one thing which we just embarking on is the application of these sound into a biomedical field for a human system, which I never thought of before. I think one of the surgeons asked me, I want to diagnose this problem without doing a CT scan for a little child or little children or little babies. If you expose them to the CT scans, then they do not know the long-term effect of the exposure to the radiation coming from the CT machine. So then he was asking, is there an alternative or is there a better way to do? It took me 5 years to realize.
Wow.
So we are putting together that ideas now. Now we have a team which includes engineers, aerospace engineers, and also medical surgeons from different hospitals, and we are seeing how we can work out that idea. So that's the answer to your question. Yeah. So sometimes some surprises will come up. Yeah.
I'm sure. If we look at, for instance, green combustion, right? Do you think we are fairly close to that being a commercially viable reality at the moment?
People are working on it. There are some companies in the US. They are demonstrating it. It is a possibility, but I think they want to lower the combustion emissions What I mean by emissions is oxides of nitrogen. So when you have oxides of nitrogen coming from the back end of the aero engines or any engines, that's going to interact with the rain, and then it can produce acid rains, like nitric acid.
Mm-hmm.
Nitric acid is not good for the environment. So that's why they have every policy government across the globe, they have a maximum value beyond which the emissions should not reach. Yeah? And that's what people will test. If you take a car for your emission test, they'll put a tube behind the tailpipe, and then they measure all these things. And the current research is being addressed towards that lowering the NOx emissions to see how we can eliminate it completely if possible. If not, how we can reduce it further below. Most of the companies, most of the research across the globe are trying to embark on that, how to minimize that one. But I think a couple of weeks back we had a discussion in the lab, and there was a new idea which came, which is telling us that we can completely eliminate it. But it's still in the head. It's still in the conceptual stage. We are going to test it and then probably develop based on that.
Got it. Yeah.
So probably that will be a game changer for some of these industries. Yeah.
Mm-hmm.
Yeah.
Got it.
So it's a great place.
And I was going through some of your work, some very heavy words that I must look down for.
Yeah.
So your research talks about connecting deep computational fluid dynamics with practical industrial applications. How do you bridge the gap between highly technical models and scalable real-world solutions?
See, at the end of the day, what we see in all of these engines is the fluid flow. Air coming in, and then you put fuel, it burns, and then the burnt gases are flowing. And this can be described very clearly. That has been done by two great scientists, Navier Stokes, in 17th century, 18th century, and those equations are written down in many places. So what CFD does, the computational fluid dynamics does, is it takes those equations, those are quite complicated equations. It takes those equations and then finds solutions for those equations, and we write codes. Okay, it's a big code that could be tens of thousands of lines or million lines, depending on how complex the problem that you're trying to look at. So nowadays, a lot of commercial codes are available as well. But the crux of what we do depends on when you mix your fuel with air, how it burns, how we can control it. There again, fundamental science, which is related to chemistry, fundamental chemistry, because fuel as a molecule, air as a molecule, the molecules interact, and how the molecules interact to create new product, and also the physics of the flow. The physics and chemistry, you cannot separate them because they interact. All these things happen simultaneously at a very fast pace, probably at the order of milliseconds, very quickly. And to understand this, you can do experiments, but experiments is very expensive. It allows you to have only certain quantities. You cannot have all the quantities that you want to develop a better understanding of the problem. That's why we apply this computational tool to calculate the flow, velocities, temperatures, scalars, concentration of various chemicals which are generated, produced in the flow as it happens. Yeah? And we run these computations in a big supercomputers for probably a week, using thousands of cores. Okay? So typically that translates to something like, if you want to do one computation, that will translate to something like 10,000 pounds
Wow.
worth of calculation. Yeah. But we do that through research projects. We apply for research money through various industries, through various government programs, through various resources. Yeah. And then we build that understanding. And then once we develop that understanding, then we translate that into simpler models, mathematical models, that can be used for daily usage in the relevant industries. Yeah? So the simpler models can help them to develop quicker solutions. For example, when they're designing a new combustor, the engineer may ask, what will happen if I change this geometry from this shape to another shape? We typically call it as a what-if type question, yeah, in engineering. So what if change this, what would be the outcome? They can find solutions to that very, very quickly. Rather than waiting for months, they can find it in a day or two. That helps them as well.
Fascinating.
Yeah, and as you may see in the citation of the Royal Academy, some of the works that we did in my lab, I have to give credits to my PhD students, okay? Because they are the one, I give them some seeding thoughts, then they make it happen. Yeah, so they develop the tools and other things. I think one of the industry was telling me that if they use the tool we developed, that helps them to save significant amount of time and money when they try to design a new combustion. So that's a very big impact for these industries, for these engineering industries.
I'm sure that's huge. And in terms of, let's say, for instance, artificial intelligence, has that played a role in your research as well? Has that kind of changed the way things have?
The word artificial intelligence is, I don't know what to take out of that.
Okay.
Yeah, that's mainly because we cannot manufacture intelligence.
Wow, that's a brilliant one. Yeah.
In my view, that's if you look at that, what people call that as artificial intelligence, if you take out all the hypey words, hypey things they put around that, look at the bare minimum, then it's nothing but simple curve fitting, sophisticated curve fitting. You have many data points, and then you want to see the trend. So what people do is they take some mathematical tool and then they apply some minimization principles to come up with a curve, which will show you the trend. And the so-called artificial intelligence, I call it as a machine learning. Yeah? Machine learning is nothing but a sophisticated curve fit. So you, instead of having one or two parameters, in your high school, for example, if you do physics experiment, you will plot x versus y. Yeah? There's only two variables. So in reality, there could be thousands of variables. So the thousands of variables can vary over a broader range, and that can be, automatically put together in some mathematical form to come up with this curve fit. And we use artificial neural network, which is again a mathematical tool, which you can train them using the data. Then if you give them a new situation, then it can predict what will happen at that situation. I believe that's what people call it as artificial intelligence. I'm not sure. I wouldn't be sure of that. Yeah. But we use this neural net to predict some of the situations that we can expect within the range of the parameters over which you trained these neurons or these neural networks. That we use it for some of our calculations as well. Yeah. So which helps, which can accelerate the computations, which can quickly give you solutions what you're looking for, or inform you with what will happen for what if type questions. But would that be the right answer or not? We don't know. We have to use the power we have, which is the brain.
Wow. Yes, I am. Just to ask you more about how you got into this engineering field, what was your journey like, and how do you, as an educator here at Cambridge, how do you lead the next generation of engineers?
That's many questions.
Yeah.
Maybe I'll try.
Yeah.
I'll try. I think how did I come to engineering? Because I didn't like medicine.
Was it the easier path?
I think so, yeah. I think when I was applying for university admissions, I got both. But I couldn't see myself as a good doctor. Now I realize that I wouldn't have been a good doctor. I can see that now. It needs a different type of personality. So that's a natural choice for me, so mechanical engineering. I did my undergrad in PhD College of Technology in Coimbatore. It's a fantastic place. I think I had a lot of good teachers to give me some insights into problems and other things, which helped me. Then I moved to IISc Bangalore, and that's where I opened up my horizon completely. Yeah, in IISc Bangalore, where I had again another group of excellent mentors, teachers, friends, and fantastic place. Yeah, I would encourage people to at least visit and see. Yeah, which opened up me into aerospace engineering, and that's how I evolved. Then from there I went to Boulder, Colorado for my PhD, and then from Boulder, Colorado I went to Sydney, Australia as a researcher with a fantastic guy who I worked with. He's one of the top in the field at the time. Unfortunately, he's no more. Yeah. So he was great. He gave me a lot of freedom, and he used to have quite a lot of discussions and fun discussing many of the problems. Honestly, the place where I learned my fundamentals is in a pub.
Wow. I would not have expected that to be an answer. Please, you must tell me more. Yeah.
I had a fantastic teacher. I think he's still alive in Colorado Boulder. He taught me fluid mechanics. And most of the fluid mechanics I learned is from him.
Wow.
Not in his class. In his class, he will turn his back and then write down everything on the board. We have to copy down. But most of the fruitful discussions happened after the class in the pub. over a beer.
Wow.
And I try to do that, not do that. I think I try to see, how that helped me to learn the subjects more clearly. So sometimes I see whether I could try that with my students. Yeah. Sometimes it works, sometimes it doesn't. So it really depends, what kind of students they come to me, what they're comfortable with, what their learning mode or the way they learn. So it really depends. So I change my style of teaching them. So it's not a unique way of only this way I teach. So it really depends.
Wonderful. So when you teach as well, are there any cross-cultural insights that, come to your mind or come to you while you're teaching? Because you have studied in India in the past, and now you're in the United Kingdom. Is there a lot of, cherry picking that also happens from the different experiences that you've had? Because you've also worked with corporates.
Yeah, I have worked for a company in Bangalore as well. So I think the cross-cultural ideas and the cross-cultural thing, it's a better way to say through an example, right? So if I am discussing some hard problem with the student, I ask them which part they do not understand. Okay? Then I see, is there an example, simple example I could draw? That simple example can come from different parts of the world. It really depends on which background they are from. And then I take that as an example and then try to explain. I don't give them the answer, but I try to draw answer out of them. Yeah. Then it stays with them.
Makes them think.
Yeah. It makes them think, it stays with them for long. If you give them the answer, they will immediately take it, and then maybe 2 days later they will forget it. But if they find an answer by themselves, it's better for them. Yeah. That's how my teaching style is. That's how my supervision style is. So far, it worked well.
I'm sure.
Yeah. So.
In this world of sustainability, a term that has come up quite often is greenwashing. How do you feel about this new jargon that's been on, I think, everybody's minds lately?
I think first of all we need to recognize that there is a problem. Yeah.
Okay.
In terms of the climate change, in terms of the global warming, all those things. What is the source of it? I think there is a different views. But many of the interpanel governmental report says that the anthropogenic means activity of the humans are the major cause coming through the carbon dioxide emissions. The carbon dioxide can come from travel, transport, cooking, various sources. Yeah, road transport, sea transport, air transport, etc. And even for power generation, for this light we need electricity that's produced somewhere else. Even there, where it is being produced, there is an emission. Yeah, but now I think what people really need to think about these greenwashing or the sustainability, or to create sustainable environment is to find a global solution. Okay? Because what happens in this room remains within this room because there are walls. But what happens in the atmosphere doesn't stay there. The wind takes it to the next country, or to the another country. If something happens in another country, it comes to us through the wind because there are no hard boundary in the atmosphere. So looking for solutions only specific to one region or one country is not going to help. Because there are so many other countries where they are still burning fossil fuels, they are doing things, and whatever the emissions they are creating there, it's not going to stay within that country. It will spread in the atmosphere. And then it will create again another problem. So this is my utopian thinking, is many governments across the globe has to come together to find a unified solution, which can happen or not is entirely another question. But if they want to find a true solution rather than a solution for the sake of finding a solution, then they have to come together and work across the border in a borderless fashion. Exchange knowledge, exchange science, exchange policies, exchange various views to build how the sustainable future can be built across the globe. That's the one which will save the planet. If the local specific countries does it, I don't know how long that will sustain. That would be my answer to your question.
And when we look at the next decade, any future trends or any engineering innovations that come to your mind that you feel will really transform the next, global energy transition that we're seeing coming in?
Yeah, renewable is catching up. Yeah, there's solar is catching up, but there is only so much they can do. In addition to that, I think the alternative form of transport. Yeah, there are so many tech solutions are being found, but most of the techs are energy hungry. None of them is energy efficient. For example, if you go to 5G, 5G is more energy expensive than 4G. Now people are going to 6G, and people are talking about autonomous vehicle. Do we really need autonomous vehicle? I don't know. It really depends on who you talk to, right? Why do you want to drive in a taxi without a driver? What are you going to achieve in the 10 minutes? I really do not know. I think people have to take a step back and think carefully what they really want in their life before we say, this would be the solution. So the game changer is, I would say that people have to think the social engineering. We have to make people realize that the energy they are using is really worthwhile. You get a quick feel, quick happiness by having 2, 3 iPhones, watching from one phone to another phone, do all of these things. But what do you gain out of it? What is that? How is that useful? What do you learn out of it? That's probably the next big thing that people have to do. Realize why they need energy, how they are, what one has to do to get that energy. So, social engineering.
Fantastic.
Developing technological solutions will happen, but those going to be, most likely to be energy hungry. So we are not going to meet the ends. These are two diametrically opposite problems. The environmental impact and the advanced technology. Advanced technology is always energy hungry. That means you need to generate more energy. More energy generation is going to create more impact on the environment unless you come up with some paradigm shift. And what the paradigm shift is going to be is anybody's guess, because there is nothing clear yet. So people are looking for that to find that paradigm shift to meet these two ends.
Just my last question. Having heard all of this, I feel that there's also been so much to unpack really, because while you were talking, my mind was racing. I was also thinking, wow, I haven't really thought about a lot of the things that you mentioned. For any average person who is watching this, right, who doesn't come from your engineering background or also could find this kind of path to be fairly complicated. And I feel that even in terms of energy, there's so much to talk about, there's so much to learn about. Where can one possibly start in terms of, trying to, say, be a more responsible global citizen when it comes to being energy efficient?
People have to have an internal, I don't want to say introvert, I think they have to do some internal analysis. Yeah. When somebody is trying to do something, they have to ask the question, is it really necessary to do that activity? Yeah. For example, to go and buy a can of milk, do you really have to take your 150cc scooter or 150cc motorcycle to go and buy a bike, or can you walk? Yeah, that's a simple question, to ask. If people do that kind of introspection, that's the word I was looking for, introspection, then I'm sure people will change by themselves slowly. And when that will happen, I do not know. And whether the governments across the globe can encourage that, yes, they can do that. Instead of building a big mall, they can build small shops, right? India was a good example, I would say. The olden days India.
Kirana stores.
Yeah, because we had all the corner shops where people can just walk in and buy whatever they want. Now they are all being moving out of the system, where we are having the big mall, fancy malls. What's the use? Tell me. Even to run the mall, you need to spend so much of energy. Doing air conditioning, you have to move people from their home to their taxis or car, and it's not helping. It's creating more problem. Yeah. So these views, these things have to be changed, and you and me cannot change it.
Yeah.
Yeah. Only the government have to think about it, and other people who are advising these governments have to give the right views, unbiased views.
Unbiased views.
Yes. And that will help. Yeah. So India was a good example before, having small corner shops. Yeah. Now even to get a cup of coffee, it's not easy in India. You have to look for a shop, which may be quite far away. But in those days, it's so easy. So people had more time to enjoy their life, but now it's not.
That's very true.
Yeah. That's the problem. Yeah. I think the introspection and then will help people to see these things. Life is a cycle or a circle. Yeah. What goes up has to come down. So things will change. Changes will come slowly. Change is constant.
Yeah.
Change is a constant. Yeah. That you can never change. Exactly right. Yeah.
Wow. Great.
That's how it is. Yeah. That's the life. Yeah. But from engineering and technology side, we try to make things better in the possible way we could. But unless people change their views and behavior and attitude, there is only so much technology can do. Yeah. That's what makes the difference. We'll see. Yeah. With that note, I don't know whether I answered your question. But,
you did, in fact. Yeah. Thank you so much. Yeah. Professor, it's been lovely talking to you. Thank you so much for your time. Had so much to learn today. And you've really been such a wonderful interviewee. And I've had an absolute pleasure talking to you and learning from you today.
Thank you for having me. As I said earlier, this is my first interview.
I'm honored. Pleasure's all mine.
Happy to be here. Thank you.
Thank you.